All right, guys, so this is part 2 of this morning's lesson. We're just plotting polynomial functions at the moment, okay? This afternoon, the last part of this is where we're going to graph rational functions, right? So you're going to have all your asymptotes and all the stuff that you've seen before, and then we're just going to layer on all of the stuff that we've done with derivative work, right? To get a better picture as to what the graph looks like on any particular interval. That's what we're practicing right now with more simple functions, right? So if we were to look at this right now, as it stands, this function f of x, okay, we want to graph this thing, label all x-intercepts, local max min, inflection points, etc. Okay, but we want to identify the intervals for which the function is increasing, decreasing, concave up, and concave down. That's what this stuff's going to tell us, right? When you start seeing words like that, you know you're finding the derivative and second derivative, okay? Now, with a polynomial function like this, we don't really have any restrictions, right? And so we can say that the domain is going to have, x is going to be a part of the real numbers. Okay, just to state that right off the top, we don't really have any restrictions of x here. We can pretty much take on anything for the domain. Okay, so we're going to rewrite f of x is going to equal 3x to the power 4 minus 4x cubed. Okay, and then we can find the derivative as being 12x cubed minus 12x squared. Okay, and then we can say, okay, well, let's find the second derivative. 12x, oops, 36 x squared minus 24x. Okay, so there's your list of, I'd say, key pieces of information that we're going to use. Okay, now we could say, all right, we know we could do one of two things, I suppose. You could find what the x-intercepts might be, right? Right. So we know that in order for this to be true, f of x, the function, we're looking for the values of the function where the y value is 0. Okay, values of x where y is 0. That's what this is saying. But that's the definition of x-intercepts. And so we're just going to say, okay, well, 3x to the power 4 minus 4x cubed is equal to 0. And we could factor out an x cubed. Oh, excuse me. And then we're going to go 3x minus 4. And that's going to equal 0. The 0 is going to consume this. It's gone. And then we can say, okay, well, 3x is equal to 4. So x is 4/3. Okay, so we have an x-intercept at 4/3. So what you can do... Oh, sorry. One thing. I'm silly. That was a silly mistake. Getting ahead of myself here. Okay. This doesn't consume this. It's one of the values that makes this work. That was an elementary mistake. Is x equals 0. And one of the values that works to make this work is x equals 4/3. Okay, so sorry. There's two values of x or x-intercepts. Okay. So then we can go down here and we can plot them. Right. We could say, okay, well, I don't know, -1 is here, -2 is here, 1 and 2. One of our x-intercepts is here at the origin. Okay, and the other one is at 4/3, which is just over 1. Okay. Now we could find a y-intercept as well. Right? We could say, okay, well, what's true about the y-intercept? Well, it's what is the value of x what's the value of y when I plug in a value of x? Okay, so that's what we're looking for. So when I plug in x equals 0 into this equation, I find out that the value that spits out is 0, right? So its y-intercept is at the y equals 0 as well. Okay, so that's how we know it's got intersects at the origin. Okay. Okay, so that's just, we're just trying to identify as many points as we possibly can from the information that's given to us, right? Right off the top. That goes to the same as the rational expressions, right? You could always find x-intercepts, y-intercepts. You could find the horizontal and vertical asymptotes if you guys are remembering these rational functions, right? So now we have another tool in our tool belt though, right? We know for critical points, right? We know that the derivative is going to be equal to 0. So we can say, okay, well, 12x cubed minus 12x squared, that has to equal 0. Okay, and again, you could factor out a 12x squared from here, right? From this this expression here, we could say 12x, and we're going to say x minus 1, right? So we can get x equals 0 and or x equals 1 again. Okay, so here are 2 critical points. We could say, even highlight this so that we can signify where we're getting all this information from, right? So we know that there is a critical point at x equals 0, and we know that there's a critical point at x equals 1. Okay, so now we can check for any points of inflection as well, right? So we can say for points, and we know what's true about this, right? Well, it's when the second derivative, is equal to 0. So take your second derivative function, 36x squared minus 24x, that has to equal 0. We could remove a 12x from there. Then we're going to see 3x minus 2 left. Okay, so again, x equals 0. Or x equals 2/3. Okay, we have a whole bunch of x values here, right? Like we have x equals 0 here. We have x equals 1, right? We could say, okay, well, what is the actual value, right, of the graph, right? So we could say, okay, well, if I were to plug in x equals 0, you know, you would get 0, 0, the origin. We already knew that. But if I plug in x equals 1 into the function, I'm going to see that I get a point of 1, -1. And so 1, -1 is going to be a critical point. What kind of critical point is what we need to define or decide on? And we can do the same thing over here, right? We could say we have inflection points, right? We know what happens when we plug x equals 0 in. We get 0, 0. And then we also know that if we were to plug in 2/3 into our equation, we'd get 2/3 and -16/27. Okay, these would just be the y outputs from plugging into the original function. So we know these are our 2 inflection points, right? We know this is a critical point. We just don't know if it's a local min or a max yet. Okay, that's determined based on what's going on around, right? So we know values like important values. We know, I'd say this is an important value. Here, let me change the color. I'd say this is an important value. The 0 is an important value. The 2/3 is an important value. Okay, and what we want to do is just check the behavior of the graph around those values, right? So, okay, well, one of them is 0. We want to check what's going on the left side of 0. So I don't know, let's plug in a number of, like, let's say -1, right? And then we could say, okay, well, one of our other important values was, I don't know, 2/3, right? And then the other important value was 1. So that's, I'm going to plug that there. And then we want to see what's going on the right side of that other important value, right? 1. So we're going to say, okay, well, what's going on? Let's just plug in 2. Okay, if I were to plug in these values into the original function, I would see if I plugged in -1, I'd get 7. If I plugged in 0, I'd get 0. 2/3 would give me -16/27. We've already seen this, most of this. -1 and then 16, right? So we have a series of points, and we could plot these and kind of get an idea. as to what the graph's doing, we could say, okay, well, -1 and 7. We could say this is count by fives, 5, 10, 15. Could say -1 and 7 is going to be up here. 0, 0, we've already plotted. 2/3 would be about here, and -16/27. That's a bit arbitrary. We could say, I don't know, down here somewhere. Okay, and then 2 and 16 would be way up here. Okay, so we have an idea, but what is the graph? What are we supposed to do, right? Like, are we just going to connect these dots and then go like this? I don't know, right? This is an important, we have something important to do here, right? And we have to check. Oh, I missed one point too, sorry. I got to plot the point. This might be a little far down. -1, or sorry, 1 and -1 I have to plot. We'll say 1, -1 is there. And then this 2/3 point is going to be about here. Okay, so are we just going to draw this curve like this and say that it's a quadratic and call it a day? No, right? We have to actually like look at what's the derivative and what are the second derivatives doing and showing us in here, right? So if we were to evaluate the derivative values, right? So now I'm looking at the derivative function, right? If I were to plug in -1 into the derivative function, I'd see that I would get a negative number out, which seems to check out, right? Like the slope at -1 appears to be negative. Okay, and then we could check. Okay, well, what's the slope? What would I get if I plugged in the slope at 0? Right? Well, I'd get a slope of 0. Right? I'd just get 0. That would be the value of the function. Right? And then if I plug in 1, or even the 2/3, the 2/3 would give me, I actually don't know what the 2/3 would give me. I haven't done that. We'll come back to this. Okay, but if I plug in 1, I'm going to get a 0. And if I plug in 2, I'm going to get a positive slope. And this makes sense, right? Because we identified these two things as being critical points up here, where the derivative should have been 0. Okay, just by looking at this now, though, it's becoming kind of clear that this is going to be a local minimum in looking at this, right? Okay, if I were to look at, like, let's say the interval, if I were to plug in, like, I don't know, let's say if I were to add a little something in here and say, what if we wanted to look at the interval between 0 and 2/3? What's going on in there, right? Well, if I check the derivative there, the slope is still going to be negative. Okay, and now we just we want to check and see, okay, well, what would happen if I plugged in 2/3? I actually don't know what would happen. I'd have to actually check that. Okay, so let's ignore this for a second. Okay, what the slope is at that particular point. It's going to be negative, it looks like, regardless, right? I would say. Right? I'd say it's negative. It's not going to be positive. So we can at the very least say that, I suppose. Okay? We only really care about the signs anyway, I guess. Right? Let's check the second derivative of things, right? These what we kind of call points of inflection, right? We've already kind of identified what they are. Okay, but this is putting a picture to the work that we've done above. So on this when x equals -1, my second derivative would equal a positive number, which is going to say, okay, well, this has to be concave up, right? This here, when 0, this was a point of inflection, right? This is a 0. We know this is a point of inflection, right? So something is changing from concave up to concave down, it appears to be, right? Because on this interval, we're going to get a negative here, right? Which indicates concave down. So I'm switching from concave up to concave down. That's why there's a POI here, or point of inflection, or turning point, right? And then it's still saying, if I were to plug actually, if I were to plug 2/3 into my derivative, my second derivative function, right, I'm going to get a 0. This is another point of inflection, right? If I plug in 1, I get a positive number. So this indicates concave up again. And then if I plug in 2, it's still concave up, okay? So now I can have a pretty good idea as to what's going on with this graph, right? So I can say concave up, you remember, looks like this, and concave down would look like this, okay? So it looks like on the interval from -1 to 0, right? So from in this portion of the graph here, right in here, it looks like the slope is going to be negative, right? Which is fine. We can kind of see that happening. But do I know whether or not to draw it like this or concave up? Well, it's telling me that it's concave up on this interval. So I could say, okay, well, it's coming in here like this, concave up. Then it reaches this point of inflection here, and it decides to change to concave down on the next interval. So it's gonna look something like that on the next interval, right? And then again, we reach a point of inflection here, right? This 2/3 value is a point of inflection, so it's going to turn around and decide to look like this, right? And then we know from 1 to 2 is also concave up, right? There it's going through our x-intercept and up and out. Okay, so this is what our graph would look like. Okay. All right. So I think we could label our minimums and all our points of inflection and everything. This would be our point of inflection. This would be 2/3 and -16/27. This would be our min. Our minimum of, where is it? Oh, 1, -1. These are our two x-intercepts. And that's pretty much it. Oh, there's one more point of inflection as well. Where are you? Oh, 0, 0. Okay, guys. So this is we're taking our derivatives and using what they're telling us what the graph should look like to actually like produce it, right? And we're just checking on this is the same work that we've been doing, just on a little bit more of a complicated level. We're looking at what are the important values. Well, the important values are the ones I've highlighted in blue, okay? And we're checking the behavior around those important values that we've identified, right? Where did those important values come from? Well, we're identifying them from setting the derivatives equal to 0. Okay, and we're creating a much better picture. You saw how if we just tried to connect all these dots, we might get something like that, right? The derivatives allow you to produce a nicer picture, a more expansive picture, right? And conclude nicer things from this. Okay, so the homework for this here, just do those 4 questions there. Okay, just try to produce some graphs for them. Obviously, you can use Desmos to help you as well. The answers are down below. You can see where everything is. Okay, so just try and follow the same process that I followed up here. Identify x-intercepts, y-intercepts, take your derivatives, set each of the derivatives equal to 0, and then you identify all your key points, and then you can just find out what's going on at each of those key points and around them. Okay, that's the gist of graphing. And it's going to be the same gist for this afternoon. It's just the functions are going to get more complicated, and we're going to introduce asymptotes, okay? And looking at what the behavior is as x approaches infinity, okay? So that's that, guys. Not too bad. I mean, there's a bit of a process there. You can follow this list. It's going to help you, okay? And I think this is section 4.5 in your textbook as well, okay? Which I believe I've posted if you need extra help, okay? So we'll see you in this afternoon's lesson.